So previously we talked about the addition principle and also its generalization, the inclusion-exclusion principle. So now we're going to talk about the multiplication principle, which is very helpful for a lot of the kinds of combinatorial objects we're going to talk about. The multiplication principle. And I'm going to state it in this way, but there's at least another way of framing this in terms of sets. I'm going to choose to do something similar to the alternative formulation I did for the addition principle, just to illustrate the point. So here's a theorem for you. So we're going to let integer, we're going to imagine we have an integer k be greater or equal to 1. Suppose k actions A1, A2, all the way up to AK are performed. If there are n1 ways to do A1, and 2 ways to do A2, and 3 ways to do A3, and so on up until and AK ways to do AK. The total number of ways to do A1 and A2 and A3 and so on up until and AK is n1 times A2, times N2, times N3, times all the way up to times NK, which of course this is equal to the product. So I'm going to use a big product to denote this. It's the product from I is equal to 1 to K of Ni. So this is the multiplication principle framed in the same way that we had our alternative version of the addition principle. If you're wondering how to prove this claim, it's very similar to how you'd prove the addition principle. Just it's just slightly different, but I think that you get the general gist of how you might go about it if you wanted to carry through the exercise. If you look at how we prove the addition principle, it's a slight tweaking of the ideas, okay? Just now we're talking about doing something and another thing, which connotates that we're dealing with multiplication instead of addition. So the big thing I really want to emphasize for you, as opposed to how we formulated the addition principle, is the fact that we have these ands here. So we're actually performing these actions. So in an intuitive way, let's say intuitive way of viewing this as a k-step process. And it doesn't have to be a k-step process in the way that you might think of literally, like I do this, and then I do this, and then I do this, and then I do this. In the same sense, what I'm referring to is that there's some action you take, and then after that, you have to commit to another choice. So that's what I'm referring to. So a common way where this appears when we talk about algorithms and analysis of algorithms, you can imagine, for example, like a nested loop. In a nested loop, you have, for example, a counter variable for each one of the loops, and then it has some number for which it occurs. So when you perform the outermost loop, you commit to some value of, say, for example, if it was I, and then say the innermost loop is J or something like that. You commit a value of I, and for that one, you commit some value of J. And you can keep going through this process. You can ask the question of how many iterations of, say, some code inside, or some instruction inside of the nested loop, how many times does that happen? You could directly use the multiplication principle on that, in the sense that you commit to some value of I and you commit to some value of j, and you ask how many ways could value I take a value on, and how many ways can j take a value on. So it's a rather intuitive thing to keep in mind. So let's do an example. So suppose that we're going to go on a road trip. Suppose a person is traveling from Winnipeg to London. And we're referring to London, Ontario, not London, United Kingdom. We're talking about Winnipeg to London, Ontario, via Sault Ste. Marie. So you got to imagine we're going on some trip. So this person is going on a trip, but they're going to be going through Sault Ste. Marie. Now, for the sake of our discussion here, I must stress that there's more than just these number of ways in reality, but suppose that these are ideal routes that we're thinking about, okay? So if there are 3 routes from Winnipeg to Sault Ste. Marie, now, you might ask, okay, why 3? Well, it doesn't have to, it's just an example, but at the same time, I must stress that you can imagine that our person is going on a trip. Maybe they're going from Winnipeg, they're going to take the route around, say, Thunder Bay and going up around the Great Lakes, down to Sault Ste. Marie. I've taken that trip. It's quite a trip. It's very beautiful. Some parts are kind of like a roller coaster, especially if you're moving or something like that. So imagine you have a person goes all the way up and around. So I don't know, let's draw a fun picture of this. Suppose I have Winnipeg here, and let's imagine we have Sault Ste. Marie here, and then we have London down here. So you can imagine you have like your Great Lakes like right around here. I'm not going to be doing this too accurate, okay? So you can imagine that one route, our participant goes up and around like this to Sault Ste. Marie. I must stress that this gap's probably a little bit more narrow. Then maybe instead, maybe my person goes down through the United States, up and around to Sault Ste. Marie, like this. I must stress that, like I said, this would be way over here, okay? I'm just doing it because I'm running out of space on this side. But another way is maybe my person is really savvy with a boat. Maybe he wants to go to Thunder Bay and just goes right across this way. So there's 3 possible routes from Winnipeg to Sault Ste. Marie. And then maybe there's 2. And 2 routes from Sault Ste. Marie to London. So for example, from Sault Ste. Marie, you might go like this, down to London. Or maybe you might, I don't know, for some reason go onto the US side and work your way around to get to London. I don't make the rules. My green friend made the rules, okay, of where we're going. That includes a boat. I'm not the savvy type to do that. Okay. But the point is that there's 3 routes from Winnipeg to Sault Ste. Marie, and there's 2 routes from Sault Ste. Marie to London. I want to know how many possible routes are there from Winnipeg to London via Sault Ste. Marie. So let me show you how you could use the multiplication principle. So you can imagine it like you're committing to a choice. I like my example I talked about with the nested loop. Pick a route from Winnipeg from Winnipeg to Sault Ste. Marie. There's 3 possibilities here, right? So you pick a route from Winnipeg to Sault Ste. Marie, then you pick a route from Sault Ste. Marie to London, which there are 2 possibilities. Now, do you see that I do this and then I do this, right? Does everybody see that? So notice that I'm going to use the multiplication principle here. And now, how many possible routes are there? How many possible routes are there? Well, it's a piece of cake. If you know the multiplication principle. By the multiplication principle, the number of possible routes is, well, we have 3 possibilities from Winnipeg to Sault Ste. Marie, and then I have 2 possibilities from Sault Ste. Marie to London. So we have 3 times 2, which equals 6. Piece of cake, right? So this is what the multiplication principle is all about. You commit to some choice, and then you commit to another choice. You think about it like a multi-stage process like this. It's very intuitive. In the same sense that, like we talked about, like if I have a nested loop, I commit to a value of I, then I commit to a value of j for like the outermost loop, the innermost loop, then I do something, right? So the number of possibilities is the product of how many possible values that first one will take on, then the second one. Just in the same way that we could talk about, I commit to a choice from Winnipeg to Sault Ste. Marie, and then from Sault Ste. Marie to London. Pretty fun stuff, right? Like our lovely person here can tell us that I don't know if our lovely green friend did actually go across from Winnipeg to Sault Ste. Marie across the Great Lakes like that. I don't know. I'm not going to ask, okay? Have not a great day. We're going to be nice. So, anyways, now that we've talked about multiplication principle, we've seen how we can apply it. I want to give you some examples of combinatorial objects, because many of them can be counted using the multiplication principle in very clever ways. But I thought it'd be a good idea to show you how you could use the multiplication principle by deriving some of these objects in terms of how many there are. So we're going to consider the following problem. So we're going to talk about selecting from n objects, k of them. So we're going to pick k of the n objects with repeats. So I'm allowed to take the same object multiple times. And you might ask, Dan, if you're taking the object, how do you take it multiple times? You're going to see what I'm talking about here in a moment. So the big thing I really want you to notice about that, so we are given n objects. We're given n objects to choose from. Each selection does not depend on the previous choice. That says the previous choice. So I want you to think about this as a k-step process, seeing as I'm picking k of them. So you imagine I have my objects. So I got my objects. So these are my objects. And I get to choose k of them, but I'm allowed to repeat them, right? So imagine I have k bins. 1, 2, 3, 4, 5, all the way up to k. So I have k bins that I can put a label for an object that exists in here. So what I'm saying is, each one of these positions, it's like me picking one of the n objects, right? But I want to label with an object. And the way you would go about this is you imagine I label bin 1 with any of the objects. So that's the first action. Then, so you label bin 1, so you pick one of these objects, you label that object for this bin. So imagine you take like a sticker, you put it on the front, and you say, this is that object's bin, okay? So you can imagine I'm going to put a sticker on front of each one of these bins that represents one of the objects I'm going to pick for it. So the first action is label bin 1. And keep in mind it could be labeled bin 2, but it doesn't matter in this case because they don't depend on the previous choice. Then you do the same. Then you do this for bins 2, 3, and so on until you get the bin k. You do the same thing. So that, just to reiterate, this says then do this for bins 2, 3, all the way up to k. So notice that you're not worrying about you could pick any of the objects for labeling the bins. So what does that mean? So how many ways can I label the first bin? Well, I could pick any of the objects, right? There's n of them. How many ways can I label the second bin? Well, there's n of them. How many ways can I label the third bin? Well, there's n of them. And so on. How about labeling bin k? Well, there's n of them. Hence, so the point is that it does not depend on the previous choice. You get to pick from n of the objects every single time, and you pick k of them. Hence, by the multiplication principle, the number of ways to select k objects from n objects with repeats allowed is as follows. Well, we said the first bin, n, many, second bin, n, many, and so on. You do this k times, right? Because there's k bins. Just in the same sense that we talked about. We make k selections. Each one, there's n ways to do it. You have k times, that means that the number of ways is n to the power of k. So remember, this is because the number of choices is n for each action, and we do it k times. That's it. That's it. So very often, a common way this pops up, so a common application of this is where, so there are objects, and any of them may appear in a bin, or you can think of it like a slot, a position. These are all just different ways of saying the same thing. With reuse, in some ordering. So you can imagine this like I talked about. You imagine it like a sequence of me labeling each one of the bins with some object. This is just some process I've decided upon. So I look at the way I could potentially do that from labeling 1, 2, 3, all the way up to K. So this could, for example, take on the form of an ordered sequence, or it could even be a plan in a day. So let me give you a couple examples of what I mean by this. So I thought I'd maybe give an example that's more tech related. Let's talk about passwords. By no means am I talking about the effective passwords. I'm just talking about some basic type of information. See, suppose that I wanted to know the number of possible passwords. Number of possible passwords of length K is equal to 6 that consist of lowercase alphabetical letters. So remember, that's 26. There's 26 possibilities here. In English, so I'm just going to make sure it's clear that this is in English, is what? Well, think of it as a process. So imagine you have your first position in the password. So imagine you have 6 positions. 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5, 6. So in each one of these positions, what can I put right here? I could put a lowercase a, b, c, d, e, all the way up to z. Any one of those could go in this first spot. So for example, so this would be your first letter. This would be 26 possibilities. Then you have your second letter. Again, 26 possibilities. And so on. So just as an example, I could have A, B, B, A, C, A, right? That's one possible way I could assign the letters. And I want to know how many of these exist. Well, as we've seen, the number of ways of assigning the first position, then the second position, and the third position, each one of these assignments is 26. So if I do it K times, how many are there? When K is 6. Well, it's 26 because I have 26 possibilities for each one of my assignments of a character. And I do it K times. What's K? 6. So it's 26 to the power of 6, which is in fact equal to, and I'm hoping that my calculation here is correct. It's 308,915,776. I'm hoping that calculation is correct. I did it by hand. Now, let's give you another example. So this is what I mean by, you can think of it as an ordered sequence. So this is just an ordered sequence. So in this case, I assign characters to 6 positions. And the ordering of them does matter. Here's another example. If you have a choice, bringing it back to thinking about meals, if you have a choice from 2, which we're going to prescribe that this n is equal to 2, from two different types of meals in the day, And the kind of meals you can have in the day are breakfast, lunch. Sorry guys, no brunch, everybody. I'm more of a brunch kind of person, but no brunch. We're just gonna have 3 here. You can always change this. Then dinner. In fact, I'll encourage you to think about adding brunch in here. For instance. So we're gonna imagine I have 3 meals in the day. I don't say that you have to, but this is just a basic example. You're always welcome to change what N and K are in the day. Then a question is, how many possible meal plans are there? So I have 2 different possible choices for the types of meals, and I have 3 meals in a day. So how many possible meal plans are there? How many can there be then? Then the number of possible meal plans is 2 to the power of 3, because each time I'm going to have a meal, again, you can view it just like we had up here. So you have your breakfast, lunch, dinner. You get to choose from meal 1 or meal 2. So you get meal 1 or meal 2 for each one of these. And you do it 3 times. Which in total, 2 cubed is 8. See, it's pretty nice, right? But yeah, that's the multiplication principle, and hoping that this will help you see how we can use the multiplication principle in a variety of different ways.